Hello everyone, welcome back. In this video, we're going to talk about the definite integral. Now, just like how we defined the slope of the tangent line to be the derivative of the function, we will also give the area underneath the curve a special name as well. And this is called the definite integral. And the definite integral is defined as follows. So suppose that f is a function that's defined on the closed interval from a to b, and we subdivide the interval into n subintervals of equal width delta x, which is given by b minus a over n. Now if we let x naught, x1, x2, all the way up to xn be the endpoints of these subintervals, then the definite integral of f from a to b is given by this notation here, and it's equal to the limit as n goes to infinity of the sum from 1 to n of f of xi times delta x, provided that this limit exists. And if it does exist, then we say that f is integrable on the interval from a to b. Now this squiggly symbol is called the integral sign, and it's an elongated s, and it's chosen because the integral is the limit of sums. Now f of x is called the integrand. A and b are called the limits of integration, where a is the lower limit and b is the upper limit. And the symbol dx indicates that our independent variable is x. You can also think of dx as being the width of a rectangle that is infinitesimally small, and f of x is the height of each rectangle. Now, the procedure of calculating an integral is called integration. Now, when we're working with the limit definition of the definite integral, then we will need to be working with sums. So here is a list of sum formulas that will be useful for us when we want to calculate the definite integral. So let's have a look at an example of calculating the areas under the curve using the definite integral. So suppose that we want to find the area under the curve x squared on the interval from 0 to 4. So the area is given as the integral from 0 to 4 of x squared dx. And by the definition, this is the limit as n goes to infinity of the sum from 1 to n of f of xi times delta x. So to calculate this integral, we will need to find delta x and f of x of I. So delta x is given by b minus a over n. So here we're working on the interval from 0 to 4. And so delta x will be 4 minus 0 divided by n, which can be simplified to 4 over n. Next, we need the x-coordinates, xi, which is given by a plus I times delta x. So we have 0 plus I times delta x, which we just calculated to be 4 over n. And this can be simplified to 4i divided by n. And the last thing we need is f of x of I. So we want to find f of 4i divided by n. So we substitute this into our function. So we have 4i over n squared, which is 16i squared divided by n squared. And so now the integral from 0 to 4 of x squared dx is the limit as n goes to infinity of the sum from I equals 1 to n of 16I squared divided by n squared times 4 divided by n. So we can simplify this to be the limit as n goes to infinity of the sum from I equals 1 of 64I squared divided by n cubed. So now we can use some of the sum formulas to help us evaluate this limit. So let's have a look at this property here. This tells us that the sum of a constant times a sub I is equal to the constant times the sum of ai. So in other words, if there are any constants which do not depend on I, then we can take that outside of the sum. So in this particular case, 64 over n cubed do not depend on I, and so we can write this outside of the sum. So this becomes 64 over n cubed times the sum from I equals 1 to n of I squared. So now we can look at the sum from I equals 1 to n of I squared. And this sum is given by this formula. So it is equal to n times n plus 1 times 2n plus 1, all divided by 6. So now let's simplify our expression. So we have the limit of n going to infinity of 64 over 6. And now in the denominator, we have n cubed. So we're going to write this as n times n times n. And we're going to write each factor of n divided by all of the different terms in the square brackets. So we have n over n times n plus 1 over n times 2n plus 1 divided by n. So we're just writing out n cubed as n times n times n, and then placing one of each factor of n underneath each of the terms, or each of the factors in the numerator. So now we can simplify this to 32 over 3 times n over n, which is 1. We have n plus 1 divided by n. That's 1 plus 1 over n. And 2n plus 1 divided by n, which can be simplified to 2 plus 1 over n. So now we will take the limit of n going to infinity, so letting n get very large. We know that 1 over n will go towards 0 as n gets very large. And so both of these terms will go to 0 in the limit. So this becomes 32 over 3 times 1 times 1 plus 0 times 2 plus 0, and this becomes 64 over 3. And so the area underneath the curve of x squared from 0 to 4 has 64 over 3 squared units. So now let's have a look at the integral from 0 to 4 of x dx. So this is the area underneath the curve y equals x on the interval from 0 to 4. And we'll calculate this area in two different ways. So one is by interpreting the integral in terms of an area, and the second is by using the definition. So let's draw the area that we're interested in. So the function y equals x is a straight line through the origin, which have a slope of 1. And we're interested in the area underneath the curve from 0 to 4. And so the area that we're interested in is going to be the area of this triangle. And so the definite integral from 0 to 4 of x times dx is going to be the area of a triangle, which is a half times the base times the height. Now the base of the triangle has a length of 4, and the height of the triangle is also 4. And so the area of the triangle is a half times 4 times 4, which gives us 8 squared units. So now let's also calculate the area by using the definition of the definite integral. So the integral from 0 to 4 of x dx is the limit as n goes to infinity of the sum from 1 to n of f of xi times delta x. So let's calculate delta x. This is b minus a over n, so 4 minus 0 divided by n, which is 4 over n. X of I is a plus I times delta x, which is 0 plus I times 4 over n, so that is 4i divided by n. Now f of xi is f of 4i over n, so we substitute this into the function y equals x, and this gives us 4i over n. So the integral from 0 to 4 of x dx is the limit as n goes to infinity of the sum from 1 to n of 4I divided by n times 4 over n. So simplifying, we have the limit as n goes to infinity of the sum from 1 to n of 16I divided by n squared. So using the sum formulas, we can take out any constants which do not depend on I, so 16 over n squared, and we're left with the sum from 1 to n of I. So now using the formula for the sum of I from 1 to n, this is given as n times n plus 1, all divided by 2. So now let's simplify. We have 16 over 2 times, we have n squared in the denominator. So we're going to write this as n times n, and we'll place each factor of n underneath the factors in the numerator. So that gives us n over n times n plus 1 divided by n. So this can be simplified to the limit as n goes to infinity of 8 times 1 times 1 plus 1 over n. And now we'll let n go to infinity. And as n gets very large, 1 over n goes to 0. And so this becomes 8 times 1 times 1 plus 0, which gives us 8 squared units, as we had from before. So notice how the limit definition of the definite integral can be quite tedious and repetitive, just like when we calculated the limit definition of the derivative. And so now in the next few sections, we're going to look at an easier way of calculating the definite integral without needing to use limits.